Have you ever stopped to think about the invisible force that, well, basically powers our entire world? It's the silent push that makes your phone battery work, and it's the unseen battle that decides if a piece of metal is going to rust away. Today, we're going to pull back the curtain on that hidden force, electrode potential. And really, it all boils down to this one simple question, right? What is actually happening inside a battery that lets it run a device? The answer, it turns out, is all about the fundamental desire of different materials to either grab onto or get rid of these tiny little particles called electrons. So here's the game plan for today. We're going to start with the electron push itself. Then we'll see how scientists had to create a universal zero point just to measure it. From there, we'll look at the two sides of that potential, build a kind of chemical power ranking, and finally, learn how all this lets us literally predict the future of chemical reactions. Okay, let's dive right in with the big idea. What exactly is this force we're talking about? Here it is. Electrode potential is all about one word: tendency. Seriously, you can think of it like a personality trait for a chemical element. Some elements are just desperate to give away electrons, while others are super eager to snatch them up. Electrode potential just puts a number on that desire. Now, measuring this tendency, well, it creates a bit of a problem. I mean, how do you measure the desire of just one thing all by itself? Turns out you can't. So scientists needed to create a universal ruler, a common zero point for all of chemistry to agree on. And this right here is the heart of the challenge. It's kind of like trying to measure the height of a mountain peak without knowing where sea level is. You just can't. You need a reference point. In chemistry, you can only ever measure the difference in potential between two things. So what did chemists decide would be their sea level? Well, they created a very special reference electrode and just assigned it this exact value, 0.00 volts. Everything else in the universe would now be measured against this. And this universal benchmark has a name: the Standard Hydrogen Electrode, or just SHE for short. Think of it as a totally neutral referee in a game. Under these really specific standard conditions, it doesn't really want to gain or lose electrons. It's just there to provide a fair comparison, letting us see which of the other elements is the stronger competitor for those electrons. Okay, so we've got our ruler, our zero point. Now we can finally start measuring those two fundamental tendencies we talked about earlier: the desire to gain electrons and the desire to lose them. These two tendencies have names. Reduction is the potential to gain electrons. Oxidation is the potential to lose them. But here's the crucial part. They're literally two sides of the exact same coin. An element's willingness to lose an electron is just the mathematical opposite of its desire to gain one. One is positive, one is negative. You can't have one without the other. So what happens if we take every element and measure its potential against our zero point, the standard hydrogen electrode? Well, we get something incredible: a chemical power ranking, a definitive leaderboard for all the elements. This leaderboard is officially called the Electrochemical series. It's just a big list that arranges elements by their standard electrode potential. That's what that little E with the circle, E0, stands for. It tells us from top to bottom exactly how strongly each element wants to gain electrons. And why should you care about this ranking? Because it's basically a cheat sheet for all of chemistry. You want to predict if a reaction will just happen on its own? Check the series. Need to figure out the exact voltage of a battery you're trying to build? The answer is in the series. It can even tell you why old ships used to have blocks of zinc bolted to their steel hulls to stop them from rusting. It is an incredibly powerful tool. All right, for our final section, let's put all the pieces together. How do we actually use that chemical leaderboard to make these amazing predictions? It all comes down to one really elegant little formula. This is it. The total voltage of any electrochemical cell is simply the potential of the cathode minus the potential of the anode. And here's a simple way to remember which is which. Reduction happens at the cathode. They both start with consonants. Oxidation happens at the anode. They both start with vowels. Pretty neat, huh? And here is the magic trick. After you do the subtraction, if that final E cell value is positive, the reaction will happen all by itself. It's spontaneous. If it's negative, nope, it's not going to happen. That single number tells you the future. So how do we actually use it? It's a simple step-by-step process. First, you find your two materials and you look up their E0 values on that leaderboard. Now, here's the most important insight. The element with the higher potential will always be the cathode. It's the one that's better at grabbing electrons. That means the one with the lower value has to be the anode. Once you know that, you just plug the numbers into the formula and you're done. So let's just boil this all down to the essentials. Just remember that electrons always want to flow from a lower potential to a higher potential. It's just like water flowing downhill. That's why the higher E0 value is always the cathode, because that's where the electrons are headed. And if that flow is downhill, meaning your final number is positive, the reaction is spontaneous. So there you have it. With this knowledge, you basically hold the keys to predicting how chemicals are going to behave. From the little battery in your TV remote to the complex dance of corrosion happening on a giant steel bridge, it all comes down to these fundamental rules. So, what reactions out there in your world can you now explain?